Today we're looking at an introduction to mechanistic interpretability. The main library we're going to be introducing today is called TransformerLens, which was originally written but no longer maintained by Neil Nanda. And it's basically a lovely little tool that allows you to easily get access to the intermediate activations of models, access to all the weights super easily, allows you to intervene and like halfway through a forward pass, mess up something with the residual stream or mess up something with a particular attention head or look at the attention patterns. Basically allows us to get like a really easy way to access the internals of the model and intervene on them to see what the downstream effects of the model actually are. So here's a sort of like origin story of interpretability for LLMs back before language models were a thing. So in around like 2015 or so, there was this project called Deep Dream, where basically you could take an already existing image classification model. I think off the top of my head they used image ResNet or something like that. And you would take the model and you would feed it an image, and then you would take a particular neuron of interest in the model, and you've some neuron that you think might be the dog neuron that responds to dogs. And what you would do is you would take the image and tweak it slightly to make the neuron maximally happy. So not just, this doesn't just get classified as a dog, but like make it the most dog-like dog you've ever seen, subject to some like locality constraints. The image doesn't become like crazy adversarial noise, and you get this like monstrosity. So you like tweak the image slightly, and it's like, yep, that looks more like a dog, and then you push it harder and you push it harder, and it starts to anything that looks vaguely dog-like in the image gets like amplified super strongly, until like you get this like sort of psychedelic Salvador Dali looking image of dogs, which I think is pretty neat. And they used to generate like lots of like surreal images with respect to some sort of concept, like cats or dogs or whatever. And the other thing you could do is you could see how like particular neurons that fire in response to something could fit together. So work by Chris Oller, described in this still circuits thread, basically found a car neuron inside an image model, and they found that the car neuron responded strongly whenever the window neuron in like the top of the image was firing, and the wheel neuron in the bottom image is firing, and the car body neuron in sort of the middle of the image is firing. And this guy would sort of listen to these three things and fire in response. So this is sort of like some sort of evidence that we believe this to be like a car neuron, in the case that if you find the inputs that this, if you deliberately train against the input to make the neuron fire maximally strong, again, subject to some sort of locality constraint, you get something that like vaguely looks like a wheel and vaguely looks like a car body and is kind of sort of a window with maybe some sort of cat-looking thing in there as well. The problem is that like often neurons might fire in response to multiple different things. This was a thing called superposition that makes it hard to really nail down precisely what it is the neuron likes. So other work done here was found that like a particular neuron would fire for I think both wolves and Coke cans for some reason. I guess perhaps it's the case that you never really see an image during training that has both a wolf and a Coke can in it, and so you can just reuse the same neuron for both, freeing up extra parameters for stuff elsewhere. That's like kind of like neat from like a perspective of learning, perspective of like the model being efficient with the compute that's available to it and the number of parameters that's available to it. But from an interpretability perspective, it's like a bit of a nightmare. If you like, you think it's a wolf neuron and you feed it pictures of wolves and it fires, you're like, great, I've like found the wolf neuron, but you don't know that it also fires in response to other things. Or maybe you try to ablate something and nothing happens because this neuron fired in response to like X or Y, and you ablate X, nothing happens, and you ablate Y and nothing happens. You're like, okay, great, I guess this neuron is neither an X nor a Y neuron, but you needed to have ablated both. So like a bit of a nightmare for interpretability stuff. So that's all well and good. And then they took these techniques and applied them to large language models, which gives us this sort of like a seminal work, a mathematical framework for transformer circuits that Anthropic wrote back in 2021. Basically, they took the same sort of ideas that were done for image models, but applied them to language models. Again, with a few caveats, you can't quite just like gradient ascent in token space as you can in image space, because tokens are obviously like very sort of discrete things, and tokens are sort of, and images are like obviously continuous things. So there's like lots of different tricks you have to do with that. You have to sort of like maybe sweep through latent space, but with constraints to be near an unembedding vector. There's like lots of little tricks that one can do. Basically what we're going to be doing today is speed running like a lot of different ideas presented in this paper and things that they found. The material suggests that you like read through this, I would weakly advise that you like skim through it and don't get super bogged down with all of the math notation. They write a lot of yucky tensor products that we are not particularly interested in because we sort of write everything as nice little einsums. And the rest of the talk is going to be presenting like a few things that they found in this paper, specifically 2 non-trivial circuits that most transformer models tend to elicit during training, skip trigrams and induction heads that I alluded to yesterday. So the 4 sort of key ideas of today is path decomposition of the transformer. So basically you can take the transformer. So remember how when I talked about ResNets, we talked about skip connections? And you can kind of think as a ResNet as like an ensemble of lots of different models, where at each layer you can either choose to run through the model or choose to take the skip connection. And so if a model with like n layers, you in some sense have like 2 to the n possible paths that the model can flow through. We're going to be thinking of the transformer in this way, where like you can take a particular operation the transformer does and break it down into the different paths it could have moved through the model. A circuit is essentially a subgraph of the transformer with the particular path that the model needs to get the job done. So for a particular task, like say indirect object identification, which we'll talk about tomorrow, we can identify the actual circuit, like these heads in like head 2 in layer 4 and head 6 in layer 9 or whatever, talk to each other in such and such way, such that if we like ablate other parts of the model, nothing happens, and if we ablate anything along the critical path, the model fails at the task. So we can sort of example actual causal evidence that we know what we're talking about. That means we can not quite formally prove, but get like pretty strong evidence, yes, this is indeed the mechanism that transformer used to like get the job done. We're going to talk again about like the residual stream being in some sense like the output accumulation. So again, the sort of intuition here is that the residual stream is like the information highway, things read from and write to. If 2 heads want to talk to each other, they'll use a similar subspace. If they don't, they'll use different subspaces. We're going to revisit the intuitive description of attention, of who asks questions, who wants to answer what they answer with. And we'll talk about, as I mentioned, skip trigrams and induction heads. Cool. Okay, so ignore the yucky math, but basically inside a transformer, there are sort of 2 main paths. If we're only talking about a 1-layer transformer, there's only really 2 paths for the input to the output. There's a direct path, which is basically you take the inputs, the tokens, you embed them, and then you unembed them directly, and you don't do anything else. So if you have a transformer that only has embedding and unembedding, the only thing it can really learn is like bigram frequency statistics. Like if you've heard of the phrase like Markovian, basically a model that can only condition on the previous token and nothing else. So if you imagine you have something that tries to predict language and the only thing it can look at is the previous word, like the best strategy you could possibly hope to do is just frequency statistics based on the previous word. These are the things that the embedding and unembedding capture early on during training, and if you ablate the rest of the model, this is basically the only thing that it can do. More complex mechanisms have to flow through the attention head itself, which can be decomposed as basically this path from the embedding through the OV, that is the product of the value circuit and the value matrix and, the value activation and the output activation, and then back out through the unembedding matrix. So we have essentially, for a 1-layer transformer, all the pass-through can be described as embedding and unembedding, plus the sum of through every head through embed, OV, unembed. And we can sort of take a particular task, because at the end of the day, the contribution to the logits is just all added up, ignoring layer norm for a moment. We can take the logit at the end and decompose it into all the contributions from each head and from the direct path. So if a particular logit got boosted up really high, the model really wants to predict the next word is like cat or whatever, we can sort of blame which head in which layer was responsible for that contribution. And what you'll find is that it's not really diffuse. It's not really like all the heads contribute a little bit. It's like one head really wanted to say a particular token, and the rest of it's kind of flat or just like adding roughly noise. So we can sort of like really nail down, for this task, this particular part of the model is responsible for doing it. Cool. Residual stream is output accumulation. So if a component in layer 2 wants to be talked to from some component in layer 1, we find that the component in layer 1 will tend to write to a similar subspace that layer 2 reads from. Recall that attention heads work in a smaller subspace, because the embedding dimension, the demodel dimension, at least for GPT-2, is what, 768? And the head dimension is, I think, 64 off the top of my head. So it's much, much smaller. So each of these components can only work in a smaller subspace. That means that things in layer 1 might not necessarily touch things in layer 2 if the layer 1 thing writes to a different subspace that the layer 2 thing reads from. This is nice because it means we can store lots of different things in the residual stream that like don't touch each other, or they could touch each other if the subspaces overlap. A particular head can also delete information and free up room for something else by basically reading what's there and then writing the negative back, which basically puts zeros in that subspace to free up room for something else. I'm going to pause here for questions. Yeah.
Is there like a good intuition or motivation for why the attention heads work in a lower dimension, or is that just like an empirical is all it works, and so we do it that way?
I mean, in some sense, they have to work in a lower dimension because the matrix is just defined that way. Like the K, Q, and V maps from D model to D head. I guess one could construct a transformer where they all map to the high dimensional space, but then I guess you might get things fighting each other, and they probably will implicitly learn a low-rank transformation.
I guess the question is like, why is D head significantly lower than D model?
Sorry?
Why is D head significantly lower than D model?
Do you want to butt in, Callum?
Yeah, I mean, so I think one intuition, and yeah, just repeat the question, was why is D head in transformers a lot lower than D model? One intuition for this is that attention heads usually are doing a specific well-defined thing, and they don't need to refer to all of the information that's stored in the residual stream. Like, for instance, maybe all that an attention head needs to do is like attend back to a name in a sequence, and maybe like the residual stream stores a bunch of information about like exactly what that token is and like exactly what context it appears in, but the only thing that the attention head cares about when it's making its patterns is like, is this thing a name? And this is usually like, this information can be contained in a much lower dimensional space than like the entire residual stream, and so usually like you only need that. It's really like just a matter of like diminishing returns from scaling up the parameter count, because like, yes, you would get more expressive attention heads, but they wouldn't really be able to like do anything that gives you enough benefit to overcome the fact that they take longer to train.
Cool. Thanks. Any other questions? Cool. Okay, we'll move on. So revisiting this sort of analogy from yesterday that we're going to be sort of looking at again to explain the behavior behind skip trigrams and induction heads. Recall that for every token, when you run through the attention module, the queries is essentially each token wants to know, each token wants to ask a question of another token. So I don't know, what token is a verb, or which ones are blue, or which ones have such and such property, which ones are in maybe like the 5th position or the position directly behind me. So these queries could be basically of any kind of thing. They could be about like the token embedding vector itself, so some property about the word. It could be about physically where the word is, so that is related to the positional embedding. And then for the key, these could respond in whatever way. They could try to communicate back, I'm in the 1st position, I am blue, I am a verb, I am like a proper noun, whatever. And then the value is what actually gets communicated back. So, which could be like the token itself, or it could be some other summative information about the token. So maybe if you ask a question, I don't know, relating to like a particular celebrity, this thing might respond with, oh, I know that celebrity, they were in such and such movie. So like the information that could get communicated back obviously is like task dependent. And then for MLPs, these are the parts where each token does processing individually. There's no cross-sequence, no movement of information across the sequence position. So whatever information's been like moved across back and forth between tokens, the MLPs like essentially allow them to process or like look up table random facts or knowledge that's been learned during training. So one of the simplest examples of circuits that were found is what's called a skip trigram. So a skip trigram is a pattern in language of the form A and then some sort of garbage B and then a C follows afterwards. So for example, if you have some text and inside the text somewhere is some mention of something being perfect and then blah, 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 the word are or the word is or the word looks, it seems like a reasonable guess to say the word perfect again. Or if you've got some like annoying little, I think this is a HTML tag, NBSP, some sort of like language markup tag. You see that tag somewhere in like the prompt, and then a bunch of other garbage, and then an @ symbol or a left angle bracket. The model might guess to put NBSP again, just because that was like a really common pattern that showed up during training. So how this works in practice is you have your 3 tokens here that correspond to the trigram. The token in the middle is going to ask the query, does anyone have a word that matches with my current word that manufactures a trigram? And down here, earlier in the sequence, the key is going to be keep if you add into it forms a trigram with mind. So this thing wants to communicate mind. Now, the issue is that due to the causal masking, keep can't know that in is ahead of it. So what you can get is sort of bugs in this fashion if you have a word that forms multiple skip trigrams. So for example, keep blah, blah, blah in mind, or keep blah, blah, blah at bay. Both of these things are valid trigrams. So keep will communicate up the information. If there's an in, mind will follow, and if there's an a, that bay will follow. And so sometimes trigrams can like screw things up and give you like guide you towards the wrong answer, because this guy ahead of time can't possibly know the words that are coming ahead. So it just guesses, I've seen keep, and I know that if later in the text an in follows, or an in or an at follows, then mind and bay are likely to follow afterwards. So I'm going to like deliver that information up into the attention mechanism, so later tokens know about it, so that if they see it, then they can use it. And if they don't see it, I guess then they won't use it, because you won't get a high dot product to match. Is that a reasonable description? Great, okay, I got the Callum seal of approval. Yeah, question?
So keep in mind and keep at bay, are those sending those replies with keys and values, are those mutually exclusive, kind of from the attention head? So if it has the keep and it says that for future reference, then in mind can be a skip trigram, or at bay can be a skip trigram, are they mutually exclusive, so that they have to kind of choose that whether it's in mind or at bay?
Yeah, do you want to button?
Also, I think there's a third slide, as in like if there's a this appears. So yeah, also like a quick general point on this. I would say that if you've not engaged with transformer architecture before, then and in particular if like keys, queries, and values still seem like a little bit alien and confusing to you, then understanding them via like the skip trigram example, I would say is like the key way to make them unlock and to, you know, for instance, intuit why values, like the information that you pass forward, are different to keys, the thing that helps you decide whether or not to pass information forward. So like understanding like what these 3 things are, the queries, the keys, the values, and how they relate to what these like the figures are doing in this analogy is like really useful. And in particular, if you can understand this and understand why attention heads lead you to these like skip trigram bugs, I think that's like a really good sign that you've pretty much like understood the key parts of attention. And so yeah, to like go back over the whole idea behind skip trigrams, the idea is that so keep in mind is obviously a skip trigram, and the model has learned the QK circuit has learned to attend from in back to keep, and the corresponding OV circuit has learned, okay, if this word is keep, then I'm going to predict like mind after the thing that attended to it. And similarly here, the word at has learned to attend back to keep via the QK circuit, and then the OV circuit has learned if the word that I'm acting on is keep, then whatever attends to it, I'm going to predict bay afterwards. But the problem is the QK and OV circuits are like 2 different mechanisms, and so if the OV circuit predicts like mind after whatever it tends to keep, and it also predicts bay after whatever it tends to keep, and if the QK circuit always attends back from in to keep, and the QK circuit always attends from at back to keep, then you can like mix and match those 2, and you can say, okay, we have keep ... Okay, this should actually say at mind, because the whole point is that this is meant to be an example of a mix-up of the skip trigram. But the idea is that you can like flip these 2 examples, and the QK circuit will still behave the same, and the OV circuit will still behave the same. But now you have this like incorrect prediction that like an incorrect reasoning step that is applied when you like do both of these 2 things. Does that make like a little bit more sense? Also, just like staring at these kind of examples and working with them as you go through the exercises will hopefully make this a lot clearer as well.
Maybe just to add to that, the really important point here is because these parts are acting in the same layer, they can't talk to each other ahead of time. So this guy will want to communicate want to ask the question, is there anything that forms a trigram, at the same time that this guy is reasoning, oh, if I see if this word in the future, this forms a trigram, I will communicate up the word mind. And so one can't act before the other. Any sort of sequential process where like if X then Y essentially has to be spread across 2 layers, because you can't, if the 2 things are in the same layer, then they're going to execute simultaneously. One can't be conditional on the other. And we'll see this in the next slide when we get to induction heads. It does do a conditional kind of thing, and so it's spread across 2 layers. And we notice this when we train a transformer that's got at least 2 layers. Usually induction heads pop up, and for 1-layer transformers, they don't. Cool. Okay. Here's our induction head example. So this one's spread across 2 layers. So for the moment, we're using the word Dursley, which is nice because it tokenizes into 2 parts, Durs and Lee. And also, this is a property that works for words that never showed up during training. So you can pick any 2 random tokens and then some random junk. And then the first of the 2 random tokens, so like token A, token B, blah, 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 token A, and the model will want to guess B, even if the pair A-B never showed up during training. Suppose there was never the phrase Barack Obama anywhere in the training data set. The model will still want to guess Obama if Barack was the previous token, assuming Barack Obama was somewhere previous in the context window. So how does this mechanism work? Basically, there are 2 parts. On layer 0, one of the heads will make every token ask the question, who is the word directly to my left? It happens to be the case that positional embedding vectors are nice rotations of each other. So there's an easy linear operation to take a positional embedding vector in position I and change it into a positional embedding vector for position I minus 1. So the question that will be communicated is my positional embedding vector rotated a bit to match the previous position. Yep.
So yesterday the positional embeddings were learned.
Yep.
There was no guarantee. So this is a different model where we're not learning positions and they are easy to rotate.
So if you're using rotational position embedding, they're hard-coded that way. If you're using learned positional embedding vectors, they happen to learn something that you can do this rotation trick on. Which is why we hard code them, because it happens to always learn rotation-y things. We may as well not waste the parameter count on it. Okay, good question. Okay, cool. I'll continue. So what was I talking about? So each of these guys will ask the question, like the actual query vector communicated is my positional embedding vector rotated a little bit. So I basically communicate up the positional embedding vector for the position directly behind me. This guy will communicate the key. His key will be his positional embedding vector. And then if the 2 have a high dot product, that means I found the guy directly to my left. So your attention pattern is going to basically be like 1 off the diagonal. Everyone looks directly to their left. And then the value vector will just be the token embedding itself, the actual word in that position. So everyone gets to learn what's to their left. Okay, and now in layer 1, each token can ask the question, what word comes directly after Durs? And then Lee knows this because Durs was communicated to him in the previous layer. So the question that's asked is basically the token embedding vector. The key is the token embedding vector that was shoved into that position from layer 0, and the value is the token embedding from that position. So everyone asks who's to the left, and then the next layer, each token asks who comes directly after Durs. Lee knows he comes after Durs because that information was transferred, and he says you should say Lee. So Lee's then communicated to Durs, which then pushes that into like the output space to eventually pump up the Lee logit, which you have, and that works for random junk. So you'll do this today, where you give 50 random tokens of garbage and another 50 random tokens of garbage. Obviously, this can't be using anything learned in the training data because there is no strategy for guessing truly random data. Except if you've seen the same random junk before in the context window, the only possible way the model could predict what comes next is some kind of approach like this. And you'll do the analysis to demonstrate, yes, it's layer X and head Y, head something in layer 0 cooperating with head something in layer 1 that does this effect. And if you snip either one of those, it totally falls apart. So you find that like the cross entropy loss over a whole bunch of examples is like really high over the first set of tokens, basically as bad as random, because of course there is no better strategy than random guessing. And then for the second set of random tokens, the loss collapses a bunch because the attention head kicks in. It's like, oh, I've seen those tokens before. They're over there back in the context window. Copy them over. So here's a lovely high-level schematic that maybe you want to stare at for a moment of the things that I just said, of how the attention head works. Again, basically, from layer 0, the only information that each token has got is positional embedding and token embedding, because there's no processing that's happened yet. On layer 0, everyone asks, what's behind me? Everyone communicates the thing that's behind them, and that information is moved from value space to output space. Again, recall that the residual stream can be considered as like a bunch of like different orthogonal subspaces, or again, like the model will learn to do this. And so layer 0 will learn to write the information of what token was there into a subspace that layer 1 expects to read back out of. So everyone copies what was there to the right, and then on the next layer, everyone asks, who is a token that follows what my token is? So the D token, or the DERS token will ask, who's following DERS? ERS will follow, oh, I follow D, here is my token embedding vector for you. That gets communicated from like the value space to some other space that the unembedding matrix expects to read from. So that way the logit for the second part of the token, the B in the AB pair, gets like pumped up. So this is like the simplest, non-trivial example of a circuit that basically always shows up quite early during training. Basically, the first thing the model does after learning bigram statistics is something like this, because in general, it's pretty useful to be able to predict a pair of tokens that's shown up previous in the context window, because this quite often makes loss go down. You should ask me some questions about this diagram. Yes?
Wait, so you're saying that every token is storing information about the previous token?
There's a particular head that does this. Yes.
Yeah, so like we are storing, so there is a subspace in every token which is storing repeated information somehow, because it's repeated, meaning that it's just the information of the previous token.
Yeah, so it's going to be the token, the information regarding the token embedding for the guy to my left gets written somewhere into the subspace for the current position. Callum's looking at me expectantly.
Oh, yeah. Oh, no, that is true. So I just want to clarify here that, like, I mean, firstly, all of this is kind of a simplification. You can think of this as an ideal case where, you know, each of these colors represents an entirely different, like, orthogonal subspace of the residual stream, and the information never overlaps. In practice, that's not, like, exactly true. It's often just, like, a useful abstraction to help us think about the, like, idealized version of what's going on here. But yeah, in practice, obviously, like, not all of the subspaces used. One other thing, if we're talking about, like, a previous token head, moving information from previous token to next token, the dimensionality of that information is limited by the head's rank. So at most, it can take up, like, you know, in GPT-2 small, 64 dimensions of the 768 dimensional space. So it's not going to, like, completely wipe out all the information that's there. But yeah, in reality, these are not, like, fully independent subspaces. It's just, like, a useful way to think about it. And as it happens, language models are pretty good at extracting information, even if it's not like occupying completely independent subspaces. I mean, you know, as an example, at the very start of the model, yeah, you just have this like token information and the positional embedding information that's added together, and these are not always like exactly orthogonal, but the model seems to be able to deal with it as if they were like two independent pieces of information.
There's also that like lovely maths fact that tells you in a high dimensional space you can pack lots and lots of almost orthogonal stuff, and this allows you to jam in a lot more information that you would otherwise intuitively think you can get away with. So like this picture maybe should have like a little bit of a blurry line in that like all of these things have a little bit of overlap, but not so much that the model can't like rip it back out. Mm-hmm. But yeah, at some point there's only so much stuff you can squeeze in. Mm-hmm. Cool. Other questions?
What's the difference between, why is the output node yellow and bluish in the first and second layer?
Okay. So this subspace here is like something that layer 1 wants to read from, and this subspace here is something that the unembedding matrix wants to read from.
So it's like directly the next token, encoding directly the next token, the yellow one?
Yeah. So the yellow thing is if you were to like use the unembedding matrix at this point, I would expect to see the logit for ERS gets like pumped way up. Mm-hmm. Yep.
Yeah, so this is like an oversimplification again, but I think the larger version of this diagram has labels for each of these 4 subspaces. But yeah, you can imagine this is literally just like the output of the embedding matrix at the start. This is literally the output of the positional embedding matrix at the start. This is literally the input for the unembedding. So you can imagine that like this thing lies in the like row space of the unembedding matrix, and these two things are just like totally ignored by the unembedding. And then finally this thing, which is like the most interesting one, is I guess you would call this like an intermediate subspace. It's something that's not directly written to in the input. It's something that's not directly used in the output. It's just something that's used to like store information as part of an intermediate circuit. And this is kind of an interesting theme that you get when you do a lot of transformer analysis, that very early on, the things that the model represents are like low-level semantic features related to like exactly what these words are. And then later on in the model, most of what the model is doing is just like making an actual prediction about what the next word is. But it's in the middle that you get all this interesting stuff where like you need to like store these intermediate representations that are like useful for like moving information around the model and reasoning about things and like doing cool stuff. And yeah, what makes this like especially challenging is unlike these two, you can't literally, unlike those two subspaces and this subspace, you can't literally examine it by looking at like the input space of a matrix or the output space of a matrix, because it is only like used by like components in the middle of the model. But in today's exercises, you'll go through like ways that you can actually see evidence of like this subspace basically.
So there's like a very, very easy way to probe for these two. By definition, this thing here will have a high cosine similarity with the first row of the positional embedding matrix, because that's exactly what it is. And this thing will have a high cosine sim with a particular row in the embedding matrix for the same reason. And this guy will have a high cosine sim with a particular row or column, depending on how you define it, of the unembedding matrix, because if we want the model to say ERS, then we want a high value for the logit in the ERS position. And the way that happens is when you multiply by the unembedding matrix, you dot product by every row. So we can probe for these directly, we can probe for these directly, but this guy's a little hard to find because I don't really have any weight I can multiply by with that would pump this thing up. So we have to use a bit more advanced tools to like find where this guy lives. Cool. Other questions? Okay, doke. The other thing that we can do to sort of find, like to verify this claim that I'm making on the spot, is by looking at the attention patterns. So for the head, the particular head in layer 0 that does the job of always looking one to the left, you can just like look at the attention pattern and you'll find that like pretty strongly all of the attention is paid one to the left, except for the beginning of sequence token, which can't do anything other than pay attention to itself. You also find token heads that always seem to look at the first position, and current token heads that more or less look at the current token. So if we go back a slide, on layer 1, each token's going to be asking for a guy somewhere in the past. And so if you have 50 random tokens of junk, another 50 random tokens of junk, what you expect to see in the attention pattern is like some line here and then some diagonal strike here, where the first 50 tokens don't really know what to do, so they kind of park their attention on the beginning of sequence token. And the next 50 tokens each look exactly 50 spots in the past. So you find this like characteristic line and then strike that's sort of like, oh look, that looks like an attention head to me. So like I said earlier, yesterday, the attention patterns are like actually pretty interpretable. You just like stare at these and get like a rough vibe of like what it is the attention head is actually doing. Yeah.
What would the trigram look like?
I expect the trigram would look like, so you want like A and then some junk B and then C. So if we jump back to the trigram one for, here we go. So the middle guy, so the trigram is A, B, and C. B should be attending to A. So I guess we would see like a big bright spot in the eighth position in the attention pattern. Yeah.
Are any, so like in the previous token head, there was like a small, like in the middle of it, there was a little like blip. If you keep going more.
Yep.
Yeah, so there's like a little blip in the middle there.
There sure is.
There are like ideal representations of these.
Mm-hmm.
Is it ever like hard coded into like the initial model?
Like we reach in there and hard code it to be this way.
Yeah, like at the start.
No. Never do this. Internalize the beta lesson of that like the GPU is cleverer than you at selecting the weights. Absolutely never do this, no. It just happens to be the case the heads will happen to learn this property if you just let them. Callum wants to say something.
I was just going to quickly check. Hands up here for people who've not read the post to the beta lesson. Okay, like some people. Sorry, I would definitely recommend reading it. It's basically like only a couple of paragraphs long, but it is probably one of the most predictive pieces of writing about modern ML that has like ever existed. TLDR for it is basically that throughout history of all ML, there have been a bunch of things that people have tried, like clever strategies to outwit the process of gradient descent and try and like create models in a way that bakes in a lot of human intuition and learning dynamics that we expect to be useful. And the lesson, time and time again, that we still have failed to internalize is like, this stuff does not work as well as throw more compute at the problem, which is very sad, but it seems to be like the way that things have shaped out.
More often than not, it is the case that like your very clever intuition of like some clever cognition that you got you want to put in the model will get wrecked by the guy with mum's credit card that has like dozens more GPUs than you do. So yeah, oops. But TLDR, never just like initialize things randomly, let gradient descent do its thing. Yeah.
How should we think about the difference between the position embeddings and hard encoding and induction? You said the position embeddings, like...
Oh yeah, okay. So one slight caveat. So the positional embeddings seem to always be the case. They want to learn easy, like sinusoidal things that can be rotated. And so these are one thing that they actually have hard-coded as trig because it happens to be the case the model always learns this anyway. But for the token embeddings, like different models have wildly different token embeddings. You want to leave that up to the model to decide.
But the like induction head, for example, like is that one we can say like every single model we ever change an induction head? So
Basically, yeah.
one in there.
Yeah. Oh, if you could, well, the problem is, if you were to hard code it, like, how do you know what subspace to put here so this guy will read from? I guess then you could hard code these two heads, but like maybe the heads do other stuff for different input. Like just let it do its thing. By hard coding, and the other problem is if you hard code something and all the attention is paid in one place, like fixed, then if there is a better thing for gradient descent to do, it won't be able to because it gets stuck and it won't be able to get feedback from other tokens. So yeah, as much as possible, like let it do its thing. let evolution like cook or whatever. Okay, is that all the things I wanted to talk about? Almost. Okay, cool. The library that we use is TransformerLens. It's fantastic. It allows you to load basically a whole suite of already existing models, not just like itsy bitsy GPT-2 models, but like Llama 2 and Llama 3 models. So like Gemma and Pythia and Phi and a whole bunch of like quite large models with all the lovely hooks attached to every head and every layer so that you can do these interventions. Which means that you can, like, if you want, repeat the same experiment of like finding the induction head on like lots of other models, and what you find is that all of them seem to find induction heads somewhere, and they all have this characteristic vertical stripe, diagonal line pattern. If you feed it 50 random tokens of junk, same 50 random tokens of junk, which is like kind of neat that like regardless of the data in which it was trained or like the architectural choices of the model, this seems to be like a universal thing that is like good for prediction, and so it is a thing that gradient descent stumbles upon quite early during training. Cool. That's all the slides I've got. So any last minute questions? Questions for Callum? Cool. All right. Well, if you got some, come talk to either of us. Get to it.